Dear friends, welcome to a first video introducing the gravity method as one geophysical method which allows you to peek into the subsurface and to identify spatial and temporal changes in density and mass. It is an important tool for many questions in the geo and environmental sciences. For example, thanks to the many satellites in orbit today, we are by now used to seeing images such as this, showing us the Earth's surface with its continents and with its oceans. And knowing the theory of plate tectonics, we also understand that continents are situated on moving tectonic plates and that those plates in turn are separated by active and by passive margins. This theory of plate tectonics is clearly instrumental for understanding the Earth's history on geologic timescales. However, I would argue that it is far from clear what the dominant driving forces are. Is it slab pull, or is it mantle drag, or maybe both, or maybe something else? And it is also unclear how these driving forces shape the landscape that we live in today. Understanding earthquakes, understanding volcanoes clearly requires that we map out the subsurface structures, and the gravity method is one way that allows you to do that even on a global scale. Another example is shown here with the Antarctic ice sheet. The Antarctic ice sheet holds a sea level equivalent of 58 meters. So even small changes in the overall mass budget of this ice sheet will change the evolution of global mean sea level, and the gravity method is one method which allows you to monitor these mass changes over time, and this provides important information for the development of adaptation and mitigation strategies to climate change. Mass changes and density changes occur over a wide range of spatial and temporal scales, and the last motivating example is shown here with this little forest. The hydrological budget of such a system is essentially the balance between the incoming precipitation and the outgoing discharge and the outgoing evapotranspiration. Evapotranspiration is hereby defined as a combined effect of evaporation at the surface and transpiration by plants, and this component is surprisingly difficult to quantify. Yet, it's an important component because it is a climate feedback. Evapotranspiration triggers the formation of clouds, and with it, the formation of local and regional weather patterns. And as we will see later, the gravity method has reached a level of maturity which allows you to map mass and density changes related to the hydrological cycle even on such comparatively small spatial and comparatively short temporal scales. I hope that these examples are motivation enough to dive into the principles of the gravity method, and the learning goals of this video are one, that you get a good grip on how the gravity method maps spatial temporal changes in density, and in order to do this you have to understand the relevant physical background, and I also suggest that you internalize at least one measurement principle, which will be the principle of a freefall gravimeter in this video. As with any other geophysical technique, the goal is to detect a target from a distance, and in the gravity method the target is defined in terms of a density contrast relative to its surrounding. Examples could be a cave, or maybe a very dense ore body that is embedded in an otherwise homogeneous host rock. The detection of this target is done with a sensor which is typically, but not always, located at the surface, and the detection works by means of the gravitational force, meaning a denser target in the subsurface would be located by detecting a stronger gravitational pull of our sensor. The physics of gravitation goes back all the way to Sir Isaac Newton, who formally defined what forces are and also who defined what the gravitational force is. And this forms the baseline for the entire field of classical mechanics. Newton inferred that a force manifests itself whenever an object changes momentum over time. The momentum p is the product of the object's mass and its velocity, and here we consider the mass to be constant, so the momentum change is equivalent to the product of mass times the acceleration g. So in that sense, the force is essentially proportional to acceleration, and this definition is true for all forces, but of particular interest here is obviously the gravitational force. Newton also found an expression for the gravitational force evident between two objects, and this force has a somewhat simple shape. First of all, it's always attractive, and it is also proportional to the two masses involved. Second, it is radially symmetric, meaning it only depends on the distance r between those two objects and not on any other directions. And third, the gravitational force decreases with increasing distance r squared. For a full quantification, we also require the gravitational constant, capital G, and this one is somehow tricky to determine. In 1798, Henry Cavendish made the first very good attempt to measure this constant, and shown here is the experimental setup. The idea was to use two well-defined test masses, and these test masses are connected with a rod, and this rod is connected at its center with a essentially thread to the ceiling. And so these two test masses can swing into and out of the plane of the screen. In an ideal world, this system is in balance and nothing will move. Now we introduce two additional test masses, two additional spheres, and we locate them offset to the plane, meaning one in front of and one behind of the original two test masses in our setup. And this now introduces a net gravitational force and a net torque, causing acceleration, meaning rotation of the two test masses out of the plane as a function of the gravitational attraction from the other two test masses that we just introduced. And this allows you, if done well, to quantify the value of the gravitational constant G. More than 200 years later, we still rely on the same principle. However, in spite of much improved measurement techniques, G is still the worst known constant in physics, and the reason is simple. It is because the experiment cannot be shielded from outside influences. Every external vibration will falsify the result, as does every horse and every student which happens to walk by, because all of these also exert a gravitational pull. In geophysical applications, G is known well enough, and so we don't really need to worry about this too much. However, it is important to realize that unlike other forces, such as the electromagnetic force, the gravitational force cannot be shielded. And as we will see later, this is a curse and also a blessing for the gravity method in geophysics. So, moving on, if we set those two equations equal, then we can isolate the acceleration g, which is measured at location m, simply due to the existence of the larger object, capital M. And in this simplified setup, let's just assume that the smaller test mass is in our sensor and the larger target is the entire Earth, of which we would like to infer the density and the mass respectively. Forces and accelerations are vector quantities, meaning they are entities with a magnitude and also a direction. However, here the direction is clearly defined by the line which connects the two center of masses of our two objects, and therefore we can forget about the vector nature for now, and we arrive at this comparatively simple expression, which, by the way, is independent of the mass of our test object. Okay, so how can we now measure the acceleration g so that we can rearrange this equation for the unknown mass of the Earth? Well, Acceleration is the temporal change of velocity. Velocity in turn is the temporal change of position. And therefore I can replace this g with the second derivative with respect to time of the position of our test mass located in our sensor. And this is a differential equation which is somewhat awkward to solve. And the reason is that the gravitational pull of the Earth changes over the trajectory of our test mass because the distance changes. And now we do a simplification. Our sensor is maybe a meter tall, maybe 2, but this is small compared to the entire radius of the Earth. So what we assume here is that we are located at the Earth's surface and that the gravitational pull of the Earth doesn't change so much in this interval of 1 or 2 meters. And therefore we can set the right-hand side of this equation as a constant, which is now determined by the radius of the Earth, which we know. Okay, and given that the acceleration is now constant, the problem is much easier to solve. If the acceleration is constant over time, then I can derive the induced velocity change via integration. The velocity will be a linear function of time. We do get an integration constant c1, which is set by the initial velocity of our test mass. And we can also get the position via a second integration. So if the velocity changes linearly over time, then the position changes quadratically over time, and we obtain a second integration constant c2, which is determined by our initial position of the test mass. Okay? And this is all that there is. The two integration constants we can simply set to 0. That's all under control of our sensor. And this means that if we measure the change of position over time, then we can rearrange this equation and isolate the mass of the Earth and also derive the mean density of the Earth, obviously because the radius of the Earth is known thanks to our Greek predecessors. Okay, this all seems simple enough. However, in the exercises, you will actually do this kind of measurement using your smartphone, so not very expensive equipment. Nevertheless, you will be able to derive a quite important first-order finding that relates to the mean density of the Earth. And I find this is a very nice illustrative example of your own home-built free-fall gravimeter. So we now return to the vector field nature of the gravitational field, which is defined at every point in space, and the length and the direction of the individual arrows indicate how acceleration increases with decreasing distance to the source. And another way to visualize this symmetry is by using circles with different radii. And once I know that the gravitational force and the acceleration correspondingly is oriented perpendicular to those circles, then I have essentially the same information content using these radii as I do using the entire vector field. However, there is an advantage to using the radii because this is a scalar quantity, so meaning it is a scalar field, and we can call this scalar field the potential field. More specifically, the potential field defines the amount of work that is required to move an arbitrary test mass against the gravitational pull of the source over a certain distance. And this work required is just a number, aka a scalar. So if I would like to calculate that required work, then I need to account for the change in magnitude of the gravitational pull along that trajectory. And I can do this using, again, an integration. So what it boils down to is that I need to calculate the scalar product of the acceleration and the line element which defines the path that I choose to go from A to B in this gravitational field. And this is more complicated set than needed because I can simply take the product of two quantities because they will always be parallel. Okay? And then I can replace the well-known expression 1 over r squared that we have derived previously for our acceleration, and then the integration turns the 1 over r squared dependency into a 1 over r dependency, and this is a scalar quantity and it corresponds to the potential field of a spherical test mass. So whether I use the gravitational pull or the acceleration field, meaning the vector nature, or whether I use the potential field, those two things are very similar and they are related either via the integration to go from the vector field to the potential field, or via taking the derivative, meaning going from the potential field towards the vector field. And here the derivative is only with respect to the radial direction because of this entire spherical symmetry. And you have to remember, you can visualize potential fields with so-called equipotential lines, meaning those are lines where the potential has an equal strength. And once I know how those equipotential lines look like, I also get a good feeling of what the underlying vector field is, because the vectors will be oriented perpendicular to that line. And the clear analogy here is if you look at a topographic map. And we will do this in the exercises so that you get a good feeling what is the relationship between the gravitational potential and the gravitational force. The gravitational potential will be important later on because there's an important equipotential line which we will call the geoid, and that is a line that approximates sea level. But this would lead too far in this initial video, and I would like to wrap up with a number of keywords, a number of takeaway points from this video. By now you should know what a force is, and you should know what the gravitational force is, and that this gravitational force is linked to a gravitational potential, which is a scalar field. Should also definitely retain that the gravity method maps spatiotemporal changes of density or mass, and you remember one measurement principle, which is the one of a free-fall gravimeter. There are others, but the principle of a free-fall gravimeter will be part of the exercises that go along with that video. There's much that needs to be done to fully understand the gravity method. We haven't really discussed spatially distributed structures. Everything that we discussed in this video is pertaining to point masses. We didn't discuss sensitivity, we didn't discuss data reduction strategies, and we will do all that. But for now, I would like to come back to the initial questions that I posed at the beginning and show you some results of what the gravity method can achieve once all those steps are successfully completed. So what is beneath the surface on a global scale? Shown here is a global compilation of a satellite mission, and there's still much you don't understand in this map. For example, what are those funny units? Milligauss. I can tell you it's a measure for acceleration, and it's an anomaly map, meaning some reference field, which we need to determine, has been subtracted. But the takeaway here is that there's a lot of variability in the subsurface, and you immediately see signatures. For example, near the Andes, there's something red, and maybe this can tell us something, whether those mountains are in isostatic equilibrium, or if they're still rising, or if something else is going on. And so those global maps, they will offer much insight into geodynamic processes. What about the Antarctic ice sheet? Well, there's a famous time series also collected by satellites. And what you see here starts in the early 2000s. The y-axis determines, quantifies the mass loss in gigatons, and the y-axis is the time, and you see an overall negative trend. That means we observe mass loss in Antarctica, and you also see some finer grained signatures, which are the seasonal component, seasonal snowfall, and so on and so on. And we even can derive the spatial signatures of mass loss, and we find they are far from uniform. There's much more ice loss in West Antarctica, and this ice loss is partially offset in East Antarctica, and there are processes that go along with that, and we can investigate those thanks to those, which I believe are fantastic results of a gravity mapping mission from space. Okay, and then last but not least, what about our little forest? Can we capture a signal of evapotranspiration? Compared to the ice loss, the many gigatons of ice lost on the Antarctic ice sheet, this component will be minuscule. However, it's also possible to determine. It takes a lot of corrections, it takes a lot of measurement time, but nevertheless, shown here is a stacked time series over day and night, and the y-axis is a measure for evapotranspiration, and you see that this changes from day to night time, which is obviously linked to the plant activity, but now we have it quantified. And I think this is quite a large step forward, and it shows you what the gravity method can do, and it also gives you an indication of the required sensitivities, because the units on that axis are something like nanometers per second squared, and that is very small, and something that goes beyond our little DIY smartphone gravimeter that we have or will build in the accompanying exercises. Anyway, with this I will finish this first video. Thank you for watching it, and please make sure that you watch the follow-up videos, which will dive into more details of the gravity method, particularly with respect to some signal processing strategies. Goodbye.